Welcome to Random Variables. In this video, we're going to talk about what they are and look at a couple of simple examples. So let's dive right into the definition of what a random variable is. A random variable takes numerical values that describe the outcome of some chance process. So basically, random variable is a variable, just like in algebra class maybe, that takes on the possible numerical outcomes of a chance process. Because going into the chance process, we don't know what numerical outcome will occur, we usually use a capital letter like X to represent a random variable. The most important thing is that random variables can only take on numerical values. So again, a random variable, just to explain it very simply, is you have a chance process. You have something where you don't know the outcome, but the outcome has to be a number. That's why we have to say it has to be a numerical value. So maybe it's as simple as rolling a die, and you don't know what's going to happen. You could get a 1, a 2, a 3, a 4, a 5, or a 6. That is the most basic example of a random variable. The random process, or the chance process, is rolling the die, and then again, the numerical values that are possible is the outcomes that are possible when you roll a die of a 1, 2, 3, 4, 5, or 6. So now we do have two very different types of random variables. They are both recognized as quantitative data, right, numerical based, but two different types. So we have a discrete random variable, and this is a random variable that can take on a countable or listable set of outcomes. So simply put, if you could make a list of all the different outcomes for your random variable, and they're typically going to be whole numbers, then you're looking at a discrete random variable. Each outcome has a probability associated with it, and all the probabilities have to add up to 1. So the most simple example of a discrete random variable is if we let capital D be the value of a die rolled once. And of course, the outcomes are 1, 2, 3, 4, 5, 6, and every one of those outcomes has a probability associated with it. Probability of rolling a 1 is 1, 6, rolling a 2 is 1, 6, rolling a 3 is 1, 6, and so forth down the line. They all have the same probability of 1, 6, and if you add them all together, you get 1. A continuous random variable, this is a random variable that can take on an unlistable amount of outcomes across some interval. So here we start to think about if the numerical outcome is something that it can involve decimals. Maybe you go to a second, third, fourth decimal place where you start to realize that the outcomes are truly unlistable. So we look at this as an infinite amount of outcomes. Now sometimes it's not literally infinite, but when you start thinking about decimal values, it certainly becomes seemingly infinite. Okay, so here it's impossible to actually make a list of all of the outcomes because there's so many of them, and because the list is so impossible to make, there is not an individual probability associated with each outcome. Now what we could do, and we could give a probability to a set of outcomes. So let me give an example. So the example I have here is S. The capital letter S is the amount of seconds Jimmy takes a shower. If you start and actually think about the number of seconds that Jimmy could take a shower, he could take like a super fast shower in 5 seconds, 6 seconds, 7 seconds, 8 seconds, 9 seconds, 10 seconds. The list seemingly goes on forever. He could even take a super slow shower that lasts, 592 seconds. And then if you start to think, well, wait a minute, what if he has a decimal amount? Like he could do a shower in 30.9 seconds or 30.91 seconds. You start to realize how that list of possible numerical values for taking a shower really does seem endless. Now what we can't do is assign a particular value a probability. Like I can't say, okay, what's the probability it'll take him exactly 32 seconds to take a shower? Can't do that. But we could, through some stuff that we're going to learn in the next couple of videos, is we can assign a probability to an interval. Like, hey, we could say, what's the probability it takes him between 30 and 40 seconds? That's an infinite interval. There's a lot of outcomes between 30 and 40 seconds, so when you start thinking about decimals, and we could attach a probability to that interval, but not to individual values. So the big difference between discrete and continuous, discrete, you can list all of your possibilities. Continuous, you can't. Discrete, you can give every one of those possibilities a probability. And continuous, you can't give individual values a probability, but you can give intervals of values a probability. So let's take a look at a couple examples here. So again, we typically use a capital letter to represent a random variable. And I like to just use X to stay generic, but you really could use anything you want. So we've already mentioned the random variable X rolling a die. That would be an example of a discrete random variable. And of course, I could list all of the outcomes for rolling a die 1, 2, 3, 4, 5, 6, and every one of those outcomes has a probability associated with them. They'd all be 1, 6. Very simple. And that's because there's, 6 sides of the die. One of them is a 4, so the probability of rolling a 4 is 1/6, and so forth, so every outcome. Another example is how many times Amy checks her cell phone during the day. Now, that would also be discrete because it can only be whole numbers. Now, that list might be long, like Amy could check it 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 times a day. But it's possible to make that list. And then, Amy could keep track, and day after day after day after day after day, she could write down how many times she checked her phone, and she could eventually figure out the long run relative frequency, the probability for each of those outcomes. Random variable x for the time for David to brush his teeth. Now, time is something that could have decimals, and there's a very long, different amounts of time. So that's another example of a continuous random variable, like we saw earlier with with taking a shower. The random variable x is the outcome of a scratch-off lottery ticket. Right? Maybe there's some scratch-off lottery tickets where you could win $0, you can win 1, you can win 2, you can win 5, you can win 10, or maybe there's a jackpot of $100,000 or something like that. But again, you could make a list of all those outcomes, and you could certainly, maybe contact the state lottery department and figure out the actual probabilities. Or sometimes on the back of those lottery tickets, they actually tell you the probabilities of winning those different amounts. Or maybe it's as simple as there's some type of game you play. Who knows? Maybe it's a video game. Maybe it's a dice game. Maybe it's a card game. It's just a game, right? And the game says that you could win 0 points, 2 points, 3 points, 5 points, or 10 points. And in the directions of the game, you could also figure out the probabilities for each of those outcomes. That would, of course, be discrete as well. So the key thing here is that, capital letters to represent them doesn't matter. Some people could use like a capital T for a scratch-off lottery ticket or a capital G for a game. Don't always have to use X, but there's only 2 different types of these random variables, discrete or continuous, and hopefully you're slowly learning the difference between them. Now, the last thing I wanted to walk you through is what a probability distribution is. So a probability distribution is any representation of the possible outcomes of the random variable and their associated probabilities. So I'm going to talk about the fact that this can be discrete or continuous, but it's usually going to be discrete, and we'll talk more about why here in a couple moments. But if I'm going to make a list of all the different outcomes and their probabilities, well, that sounds like a discrete random variable, because remember, continuous, the list is way too long and you can't actually list all the outcomes. But there are some tricky ways that you could do that, even if it sounds pretty hard. But a probability distribution could come in the form of a table, a graph, or a function. Now, what's awesome is that with a probability distribution of a random variable, we could discuss the shape, center, and spread, much like we learned back with quantitative data. Because when you're working with quantitative data, which random variables are quantitative because they're all numerical based, you could talk about the shape of the distribution, the center of the distribution, and the spread. And there'll be later videos that go over that as well. And the cool thing is when you have those 3 things to talk about, it makes for great discussions about a particular population of interest. So again, a probability distribution is simply nothing more than a graph, table, or function that tells you the different outcomes of the random variable and their probabilities. So let's look at one really, really quickly here. So the number of tickets purchased by a customer for a musical performance at a certain concert hall can be considered a random variable. How many tickets are you going to purchase? 1, 2, 3, 4, or 5? Nobody purchased 0 because if you're purchasing 0, you're not going, and nobody has ever, maybe they just don't allow you to purchase more than 5. And again, we notice that we have probabilities underneath them. So this is long run relative frequency. So over the course of many, 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 many shows at this particular hall, we know that there's a 45% chance of selling 2 tickets or a 5% chance of selling 5 tickets and so forth. So again, pretty simple example of a probability distribution. Here's another one that is more of a graphical base. So when a book editor edits a book, they often look for how many major changes are needed. So let's let S represent the amount of major changes needed. And we see here that sometimes there's 0 major changes are needed, right? And you could look in the table and see that happens maybe at about 13 or 14% of the time. Sometimes 2 major changes are needed, 1 and then 2 would be right here. Those look to be about the same probability, maybe somewhere around 26, 27%. But again, it's just a way of me showing you the outcomes. That would be across the x-axis and the associated probabilities with each one of those outcomes. Instead of me just telling you the number, I give you a graph that you could kind of figure it out. Now, the only bad thing about a graph like this is that you kind of have to make a rough approximation that this would maybe be 27%, this would be 27%. But at the end of the day, if you estimate each one of these bars, they better all add up to 1, because they all have to add up to 100%. So that's another cool example there of a probability distribution given to you as a graph. And one more example we will look at here. Here is a probability distribution for T, the amount of time in minutes it takes Josh to get to work each day. So Josh has every time he goes to work, who knows how long it takes. This would definitely be a continuous random variable because it could take him 5 minutes and 3 seconds, 5 minutes and 4 seconds, 5 minutes and 32 seconds. And then you could even got decimals on that, right? 5 minutes and 32.6 seconds. That's what makes the list pretty endless here. Now, because it's continuous, we see this curve to represent the distribution, where we see somewhere between 1 and 2 minutes is the most likely. And this is what I was saying about earlier with a continuous random variable. I can't tell you the exact probability of 1 minute or the exact probability of 2.5 minutes. But I can say, hey, if I look in between 1 and 2 minutes, it looks like there's a really big chunk of data there. And we could, through the use of some technology and some stuff that we're going to talk about later, we could say, hey, I estimate that maybe somewhere around 35% of the time it's going to take him between 1 to 2 minutes to get to work. And the other cool thing is we definitely see the shape here, right? And we saw that earlier with this one. We just didn't mention it. We'd say that's skewed right. Most of the time there's, 2 or 1 major changes. Very few is there going to be 6, 7, 8 major changes. Same thing I could say here. Most of the time it's going to take somewhere between 0 to 4 minutes for Josh to get to work. Way less likely for take 4, 5, 6, 7, 8, 9 minutes to get to work. But on occasion, maybe traffic or bad weather, it might take more than 9 minutes, but extremely unlikely. So that's why we see that it's very, very less over here on the right-hand side. So again, these are all different ways that we can look at a random variable. Across the x-axis is the outcomes. Even if it's continuous, we just make intervals, as opposed to here we just have the actual whole numbers. And then of course we could use a table to just tell you the probability of each outcome. We could use bars to show you the probability of each outcome, or we could use a curve like this, and you're going to have to do a little bit of estimating for the probability of each interval within that graph. And that's where it actually gets a little bit harder, and we're going to have a lot more discussion later on in future videos about continuous random variables. But hopefully by the end of this video you have a really strong sense of what a random variable is. It's basically like a variable in math class or an algebra class. You don't know what it is, but you know the potential values that it could take on. Discrete or continuous, pretty simple, hopefully nice and easy.